Hello everyone. In part 23, which is also related to Wittig reaction, and here application and problems related to Wittig reaction will be discussed. Wittig reaction I have started from basically part 20, that is 20, 21, 22 and 23. Total 4 videos will be there. You can find the other links which will be appearing on the screen, and you can also find in the description box the playlist of nucleophilic addition to carbonyl. In that also you will find all these 4 videos. Okay, so let's start. Now when we are talking about application, there is basically different applications we will see, and it is a very good method to prepare alkenes that are difficult to prepare when we consider the other methods. So that is why this reaction, it has very important application for the preparation of CC double bond. The first point here we have the example where we are making exocyclic double bond. Now as you can see here we have carbonyl group, and here the carbonyl group that is changed to CC double bond. So this type of exocyclic double bond, that is double bond which is present outside the ring, it is very difficult to make by other processes. But when we consider Wittig reaction, we can make it very easy. Here the phosphorus halide that we have taken is CH3 P plus PH3 and potassium tertiary butoxide, which is basically very strong base. In presence of this strong base, there will be carbanion generation at this carbon by removal of one of the hydrogen, and ultimately the halide that we will get is CH2 minus PPH3 plus. So this CH2 minus that will be attacking at this carbonyl carbon, and rest of the mechanism as it is. Okay, mechanism you can obviously find in the original video of Wittig reaction, that is part 20. So here we are getting CC double bond, and this is exocyclic double bond. Next example, now we will prepare beta gamma unsaturated acid. Now this is something unusual. Normally we are habituated to see alpha beta unsaturated acid, like, okay, because alpha beta unsaturated acid, that is more stable because resonance is present. So alpha beta unsaturated acid will be like this. With respect to CO2H group, this position is alpha, this position is beta. So we are calling it alpha beta unsaturated acid, and because of resonance this type of acid is very that is stable. So its preparation is also easy. But suppose if we want to make beta gamma unsaturated acid like this. Now with respect to this carboxylic group, though here it is in CO2 minus form, but it is actually acid. This is alpha, this is beta, this is gamma. So now the position of CC double bond is not alpha beta, it is beta gamma. And this type of unsaturated acid, it will be difficult to make because there will always be a tendency to that it will be converted to, from beta gamma it will be converted to alpha beta. Okay, but if we follow Wittig reaction as it is very selective, so here we can get beta gamma unsaturated acid and there will be no alpha beta unsaturated acid. Now for the halide that we have taken is PPH3 plus, then CH2 CO2H. Now if you are thinking why it is in minus form, basically the previous step if we write, it will be, that is just add one hydrogen here, it is like this. Now when we are acid strong base, then this one of this hydrogen will be removed and there will be generation of carbanion, this carbanion. But as this is also, this hydrogen is also acidic, so that is why there will also be a negative charge. But that will create no problem. Reaction will be only at this carbon. So 1, 2, 3. 3 carbons are now added to this carbon, and ultimately we are getting this beta gamma unsaturated acid. So this part is coming from R2CO, that is carbonyl compound, and the rest of the part is coming from halide. Okay, and this is the byproduct. Here it is not mentioned. So in all other methods there will be a probability of isomerization from beta gamma to alpha beta because that is more stable because of this resonance fine, which is not possible in case of beta gamma unsaturated acid. So this unusual acid that we can make by this method. Number 3, synthesis of cyclic alkenes containing 5 to 16. See, this is a huge number, right? As minimum as 5, which is very small ring, up to 60. So see, this variation, that is the range of number of carbon, this is very high by intramolecular Wittig reaction. So intramolecular Wittig reaction means now the carbonyl group and the ylide part both are present in the same molecule, and this number of N that can vary. Here this carbon will be attached to this carbon, that means 2 carbon. So N value that will be minimum 3 is possible, because from 5 2 carbon we already have here, so 3 more will be here. So 3, starting from 3, it may be up to 14 also, because 16. So 2 carbon already here, 14 carbon more. So here intramolecular Wittig reaction, that is even if there is any other groups present, suppose if it is not CH2 whole N, suppose there is any other group, then also there will be no such problem, because this reaction is very selective. This carbonyl, it will only react with this carbanionic part of ylide. It will not react with any other part. So ultimately what we are getting, this type of ring structure, and depending on the value of N, we can get different number of rings. Number 4, carbonyl compounds may be stepped up to aldehyde, that means containing 1 more carbon. Here we have taken pH, COPH, okay, and the ylide that we are using, PHTP plus CHOMe. If we move backward, it will be produced from CH2OMe. Okay, you will use some strong base, there will be generation of carbanion, and ultimately we will get this type of ylide. So in this ylide, this part will be attached to this carbonyl. Okay, so the alkene that we will get is this one. Okay, now it is, see, there is CC double bond as well as it is ether. So you can see it is one type of enolic ether. Okay, so this alkene, which is the Wittig product, if we are treating it with H3O+, that means you are doing hydrolysis in presence of acidic condition, then it will be converted to this type of molecule. So now it is PH2C, then CH, that means 2 carbon, and ultimately if we compare with the previous carbonyl compound, that is before reaction, here we have without pH group we have only 1 carbon, but now it is CH. That means we have started from carbonyl compound, it is stepped up to aldehyde, because it is aldehyde and it is containing 1 extra carbon. So if we want to make, that is if we want to increase 1 carbon, then we can also apply Wittig reaction. Now if you have any doubt that how from this molecule by acidic hydrolysis we are getting this one, then I will show that in the next slide. Here the alkene that we have obtained from Wittig reaction is this OMe, right? There is lone pair. Now we are treating it with acidic condition and water. So this type of mechanism will be there. Now it is PH2CH. Oxygen is positively charged. Okay. In the next step, water will attack here. Oxygen will be neutral again. PH2CH. CH. Now oxygen of water is positively charged. There is proton exchange. So this hydrogen, if it moves towards this, basically the direction of arrow, it will be not like this. PH2 CH OH, then O, Me, and hydrogen attached. Now this oxygen is positively charged, and finally what will happen? This CO bond will be broken, So there is double bond O and H, and here minus methanol as well as minus H+. So ultimately we are getting PH2CH CHO, and here you can also see it is also PH2CH CHO. So in this way, that is the final product that we are getting. If we do acidic hydrolysis, then we can get aldehyde with 1 carbon extra. Number 5. Now this is very interesting. See, we can make even allenes. So allenes are basically the structure where you will have this type of CC double bond adjacent position, and for this we have taken ketene as starting material. Okay, because if we take ketene, then only we can get allene. So here normally we take carbonyl compound, right? But here already some CC bond is present. Now when we are using this ylide, this part will be attached to this carbon. Okay, so ultimately we are getting PH2C double bond Cl2, and this is the byproduct. So when we want to make allene, we have to start from ketene, not any other carbonyl compound. The reaction may be used for chemoselective insertion of double bond. Why it is chemoselective? Because other carbonyl groups, suppose other carbonyl group which is from amide group or ester group, that will not react because it is specific only for normal carbonyl group, that is either ketone or aldehyde. So the starting material that we have taken, here we have amide, we have ester, and we have normal keto group. Okay, and we are using the ylide. So here this ester group will not react, amide carbonyl that will also not react, but only this here will react. So as a result, this part is intact, this part is also intact, only this CO C double bond O, that is now converted to C double bond CH2. So this is chemoselective. There are 3 carbonyl groups, but only 1 carbonyl is reacting, taking part in reaction, not the other 2. Now we will see some problems. So here we will move backward, because directly the structure of alkene is given, that is CC double bond is given, and we have to write the structure of the organic halide from which we will make the ylide and the carbonyl compound. So we have to move backward. Now when we are moving backward and you are breaking the CC double bond, basically there may be 2 possibilities. Either you can write the ylide which is from the left hand side, or you can consider the ylide which is from the right hand side, and the other part that will be served as carbonyl compound. But remember, here the ylide we are making from organic halide. By which mechanism? Mechanism we have already discussed in the original Wittig reaction video, that is part 20. You can also click on the link appearing on the screen and see. This is by SN2 mechanism. In general, the ylide should come from an unhindered alkyl halide. Why the alkyl halide should be unhindered? Because it is going through SN2 mechanism, and in SN2 mechanism the alkyl halide, if it is sterically hindered, then the mechanism will not be possible. Okay, so SN2 is single step reaction, so the transition state it must be unhindered. PPHC, it is already a very large group, so when it is attacking from the opposite side, this halide, it must be as less hindered as possible. Okay, and finally we are getting the ylide. So when we will do the retrosynthesis, we have to see that from which part we will be able to get the unhindered alkyl halide. Now when we are moving backward, if you are writing the ylide from the left hand side part, see this part is more sterically hindered, so that will not be correct. So that is why when we will move backward, we have to take carbonyl from left hand side, and right hand side part will be ylide. Basically the ylide structure, if you write, it will be like something like this. Okay, but if you want to write organic halide directly, it will be CH3Br. But you can also write it directly, that is without writing ylite. And how you can do so? What you will do, the right hand side part is CH2, so just add 2 bond. I am trying to say just add 2 bond, one will be H, another will be X, that is halide. It may be Br or Cl. Okay. Now see, even you don't have to write ylite. Suppose if you are getting this question in examination and if you are lacking in time, then obviously directly you can write this structure, that is CH bond and CX bond, because when we will be using CH3X, that is I'm talking about this halide. First, what will be happening? PPH3 will attack, so X will be removed as leaving group in the SN2 mechanism. And in the next step, what we do? We use base. So here when we use some base, then one of these hydrogen from this carbon will be removed. So basically it is removal of X first and then H. So that is why we can add directly CH bond and CX bond. Fine. Next example, let me erase it. PHCH and CMe2. So in the left hand side we have one PH and one H, and in the right hand side we have 2 methyl groups. So this side is more sterically hindered, so we will take ketone in the right hand side and halide in the left hand side. PHCH, just as I have said, add one H, one X. So this is your alkyl halide. This is basically benzyl halide, right? PHCH2X and carbonyl. Next one. Now we have 2 double bond. So here, which part will be less sterically hindered? It is a symmetric molecule, right? So you can consider any of this side. But this side we have PH and H, but this side is very large. Okay, so obviously it will be PH, CH, just add hydrogen and X. Again, the same molecule as in example 2, that is PHCH2X, and CO, CH. Fine. Then the third one, here we have H, and this side we have 2 alkyl group, that is it is a cyclic molecule. So we will prefer keto in the left hand side, because here if you consider the left hand side part, here we have smaller group hydrogen. CO2ET, H and X. Okay. So this is basically what type of molecule? It is halo ester, halo substituted ester. And the last one, here we have H and OPH group attached with carbon, and this side we have 2 PH group. So obviously left hand side part is sterically hindered, so we will take carbonyl in the left hand side part, and less sterically hindered part will be the halide. Okay, so in this way we can do the retrosynthesis. This is the last problem we will discuss today. In this compound, first we are treating it with PH3P, 1 mole. See, it is clearly mentioned how many moles. We are getting compound X. Then 2 moles of PHLI we are getting Y, and finally we are treating it with PH2CO, and the final product is Z. So first this PPH3, it will attack one of this carbon, and there will be removal of bromine. How many carbons are there? Just count. 3, 4. Okay, 1, 2, 3, 4, and then PPH3, and this PPH3 phosphorus is positively charged. Okay, now next what we are using, this is X. Next we are using PHLI. Now these 2 hydrogens are acidic in nature, so when we are using PHLI, it will capture one of these hydrogen, and there will be generation of carbonyl. Now this carbonyl it can attack here because there is a good leaving group, bromine. So these two carbons will be joined and we will get 4-membered ring. pH 3 plus, phosphorus is still plus. Now there is still one hydrogen and this hydrogen is acidic because of this electron withdrawing group. So next molecule of PHLi when we will be adding, then this pH will capture this hydrogen and there will be formation of carbonyl. So this is the elite, right? Let me change the color. Now we have taken pH, CO, pH. This negative charge will attack here and we will get pH2 CO, then okay, and there will be okay. So these two part, that is, remember, first betaine structure, then oxaphosphetane structure. 1, 2, 3. CO. Okay, let me count it. pH to C, it is, sorry, I have written the wrong structure. It is not like this. It is directly attached to this carbon. Okay, and here we have this cyclobutane ring. So always when you are doing this type of mechanism and there is a confusion of number of carbon, it is always better you number the carbon. Okay, so just like this, that is 1, 2, 3, 4. Okay, so C, that is carbonyl carbon, that is now attached with 1 carbon and this is 2, 3, 4. So in this way you can avoid the errors. So I am directly joining it here. Ultimately what we will get CC double bond and POPPH3. So this is number 1, 2, 3, 4. Okay, so this will be the final compound. CPH2, it is attached in exocyclic double bond and this is Z. And which one is basically Y? This is Y. That is the elite, that is actually the Y. Okay, I hope you will find this video helpful. If you find it helpful, please like, share and subscribe. I will meet you in the next video. Thank you for your time.